a very warm welcome to all our younger friends here. I'm Robert Dijkgraaf. I'm the director of the Institute for Advanced Study. For those who haven't been here, this is a independent research institute where typically on an everyday the most difficult mathematics is being discussed. But I think we have, in many ways, the most exciting audience that we could have, because I really see here people at all different ages. I must say, the first time we had a lecture here, the youngest participant was 5 weeks, and the oldest at that point was our very famous professor here, Freeman Dyson, which I rapidly calculated was roughly 5,000 weeks. So that's already the theme that we'll be talking about. We're talking about mathematics, about counting, which is, I think, something we can all relate, young and old. And we're particularly happy that we have an excellent speaker, a very distinguished mathematician, Richard Schwartz, who's in his everyday life is a very distinguished professor at Brown, doing very, very complicated things, but has also a very strong connection to the Institute. Rich, you got your PhD here in Princeton, actually. You were here with your family, who joined him here today at the Institute in 2003, and apart from being a very, very good mathematician, Rich is kind of exceptional in the sense that he writes these absolutely beautiful books, which you can actually kind of buy here, and I strongly recommend, about mathematics. And the first time we actually met was last spring in Washington. We had the so-called National Mathematics Festival, really celebrating mathematics in all different forms and shapes. And one of the things we did there is award prizes for children's books that address the issue of mathematics. And Rich, you were one of the laureates. And so when I saw your book and here to briefly talk, I think, well, we should get you here down to the Institute. I think it would be very appropriate. This might be in many ways your most challenging audience. And I would really watch out for the very small children, because they will ask the most difficult questions. I think that's... So we'll have a lecture, we have some Q&A afterwards, and then of course you're all invited also kind of to join us here for lunch. And those who do not know the Institute, perhaps you know there are the beautiful woods around us. They're publicly accessible, so it's a lovely day. So I would say take a healthy shot of mathematics and enjoy some great food, and then the outdoors, and then you have a terrific start of your weekend. Thank you so much for being here.
Okay. Well, it's really a pleasure to be here. When I was here 12 years ago as a member for the year, I think it was just one of the best years of my life. My grad school years were, well, they weren't as happy, they weren't as great as that, but they were still pretty good. So I thought the first thing I do is I would have all the kids actually do something. It was something I used to like to do. My friend and I used to like to do this in college. So what I want you to do is take, if you have a piece of paper and a pen on it, I want you to take, in 30 seconds, I want you to write the biggest number you can. So I'm just going to say go, and then do it. So I'll wait a minute, I'll wait a second till you get the paper out. And I've reached the age where I can barely read the second hand. You guys ready? Set. Oh, wait a sec. Okay. Ready, set, go. Okay, now you have 15 more seconds. Okay, almost done. Stop. Okay, now I hope to get to look at some of these afterwards. And maybe afterwards you might want to try it again after you see some ways of writing really big numbers. So one thing I did, this little chart here, this is, I always, whenever I used to, still when I go to talks, frequently I'll just get lost after about 5 minutes. And most talks look like this, although usually there's just one arc that kind of goes up. So this talk, it's going to sort of start out easy and like my book, and it kind of gets harder. So if some of you little kids get lost, you should wait for the cow named Gracie right in the middle of the talk. In a way, it's going to start over, and then it's going to kind of start from the beginning again. So that's sort of the, this is a little plot of the time versus the difficulty of the talk. OK, so well, this is me when I was a kid. I used to like to, in the beginning of my book, I talked about why I became a mathematician. And then I've matured many years, and this is me now. Sort of, when you're a mathematician, you basically get to do the same thing you did when you were a kid, if you liked numbers. OK, so the idea I had for the book was sort of like the numbers are a little bit like a ladder, and you kind of go up and you count, and initially it goes kind of slowly, and then it accelerates. So I thought what I would do, at least for the first part of the talk, is sort of show you some numbers and as they get bigger and bigger. And then the second part, I'm going to talk about kind of infinite numbers in a way. OK, so this is sort of the beginning of this. You could picture numbers as dots. There's 1, 2, 3, et cetera, up to 9. And then there's there it goes all the way up to 90. This is in here. This is what 90 dots looks like. Well, someone in the audience had found a mistake in the published book. There was only 70 here, and so for the talk, I changed this slide and I fixed it. OK, so these are some small numbers. This is what 100 dots look like. I'd sort of imagined as I was writing this, if you had 1,000 dots, you could replace each one of these things with one of these. You count this way, you get these kind of flowers within flowers kind of look. Anyway, that's what 200 dots look like on the left. So then this is me a little bit further up on the ladder, getting a little bit, you get a little bit tired of counting slowly, so it picks up. This is what you'd get if you took a cheese cube and you cut it into 10 little slices in each of the 3 directions. What's going on is 1,000 is 10 times 10 times 10. So if you cut this thing up into pieces, you get these little cheese cubes. That's what 1,000 looks like. So I was sort of trying to, the idea is to kind of picture what numbers are like. So this is what 2,500 dots looks like. And it says these, I don't know if you can barely read it, these pages, or this page, anyway. So each one of these grids is 100 dots, and then you have a 5 by 5, you have 25 of these 100 grid pieces. So that's what, if you wonder what the number 2,500 looks like, that's what it looks like. OK, here's a way to think about 1,000,000 dots. You imagine that you have one of these things on each page of a 400-page book. And so that's what a 1,000,000 dots looks like, roughly. That you could say, well, how big is 1,000,000? It's sort of like you have kind of like a thick book that's just filled with little dots. And then there's me on the ladder, sort of moving up. OK, so here's 7 billion. It's 7 with 9 zeros after it. That's about the number of people on the Earth. And I calculated, based on about how tall they are, that if they made a ladder off of the planet, they'd go about 1/4 of the way to Mars, at least on the day when Earth and Mars are as close as they can get. So that's, yeah, question? Well, I just mean when the Earth and the, when they're moving around the sun. I don't know the date, but whenever they're, I mean they move around. They're moving around, and sometimes they're further apart, and sometimes they're closer. So I wasn't. When they're, you've got these balls moving around, and whenever they are closest, that's right. OK. All right, 20 billion grains of sand in a basketball. So, well, when I wrote the book, I had some idea of, basically I drew the pictures and I wanted to put them in some order, so I had to get the numbers right. So I guess it depends on the size of the grains of sand. So anyway, for very fine grained sand, That's about the number of grains of sand you could fit in a basketball. Okay. And now this is 100 billion. This is the number of basketballs that would fill up New York City, basically, to about the height of a person. Just imagine the whole city filled up with basketballs. And there's me with some special cufflink from All Souls College. Okay. So now I want to talk a little bit about how you write big numbers. Here you saw that I was writing 1 with a bunch of zeros. And this way of writing numbers is a shorthand. You take a 10 and then you put another number on top, and it tells you how many zeros to write. So 10 with a 3 is 1 with 3 zeros, and 10 with a 6 is 1 with 6 zeros, and so on like that. So here you've got 1,000 and a million, and then a billion and a trillion. And then it goes on. There are these funny names, which I didn't include, but then the next one, 10 to the 15th, would be called a quadrillion. And then there's a quintillion and a sextillion and a septillion. There are these funny names. Actually, in the book, there's a whole bunch of these pages, but I didn't include them. So moving a little faster, this is about 10 to the 50th, 1 with 50 zeros. That's about the number of atoms there are in the Earth. And I'm not going to say what an atom is, but the way to imagine it is that there's someone, actually this isn't a very pleasant image, but imagine someone is coming from the outside with sort of a giant squeezer, and then they just kind of crush the Earth, and they just keep kind of pulverizing it into the smallest constituent particles they could make, even smaller than grains of sand. So this is what would happen, more or less, as people went along. They sort of, eventually, it would just be kind of moved down to these things which really are some way that people might represent atoms. So there's about 10 to the 50, 1, 0, 0, 0, 0, 0, 0, 0, etc. atoms in the Earth. For comparison, this is a much larger number, 10 to the 61. So it's like it's like a billion times as many as the particles in the Earth. It's what a traveling salesman path is. These are 48 dots. And what you do is you're allowed to start somewhere, and then you're allowed to go to some other place, and then another place, and then another place, and eventually just visit all the places and then stop. And so imagine if you were planning a trip to all the capital cities. Realize I can't remember any, but like maybe Boston. First you go to Boston, and then you go to Sacramento, and then back to Providence, and so on like that. So a way to think of it is you get, there's 48, and you get 48 choices for where you start. And after you've made that first choice, you get 47 choices for where you're going to go next. And then after you do that, you get another 46 choices, and so on. So if you think about all possible ways, it's 48 times 47 times 46, et cetera, et cetera, et cetera. So you're taking like 48 numbers and you're multiplying them together, and most of them are much bigger than 10. So you're getting something which is bigger than the number of particles in the Earth, number of atoms in the Earth. So anyway, that's a big number. Then there's a much bigger number. It's called a Google. That was the name of this before it was a search engine. 1 with 100 zeros. And a Google is roughly, this was a hard one to get right. This coffee cup is supposed to represent the observable universe. I guess for all we know, the universe is infinite, and there's an infinite number of particles in it. But there's some speed limit to how fast things can go, and you can't see everything in the universe. There's some sort of section of the universe we could theoretically see, and there's about maybe 10 to the 80th particles in it. So somehow a Google is like a number that's a little bit bigger than sort of what's in our observable universe. So how to think about a Google? Well, here's one way I thought of it, sort of like it's a little bit like the traveling salesman idea. You imagine this guy's painting a picture, and he's making his picture on a 10 by 10 grid, and he's allowed to use 10 colors. So for each of the 100 squares, he's got 10 choices for which color to paint it. So he's got 10 choices for this one, and then 10 for the next one, et cetera. So it's 10 times 10 times 10 times 10, et cetera. And if you think about how that works, it gives you, like 10 times 10 is 100, which is 1 with 2 zeros. And then times 10 is with 3 zeros. And so if you do 10 times 10 100 times, then you get this number 10 to the 100th power, a googol. So a googol is like the number of different 10 by 10 paintings you could make with 10 colors. So actually, when you think about it that way, in a way, it's kind of small. Like if you think about all the books you could write or something, or the paintings you could make, you have many, many more choices. OK, so now there's a number called a Googolplex. So a Googolplex is 10 to the googol power. So this number is 1 with a googol zeros written after it. If you sat down and you tried to write this number in ordinary, just with the zeros, it would, would sort of fill the known the observable universe, even if you made the zeros really, really tiny. So just to write the number, let alone what it means, basically, well, you couldn't do it that way. And you could ask, like, how do you picture a Googolplex? And as I'm going to illustrate with the next couple slides, you can't picture a Googolplex. But here's a way to say it. Imagine you had an alphabet. So in our alphabet, there's 26 letters. Imagine instead you had an alphabet that had a googol letters in it. So you could think of each of these 10 by 10 paintings that you were doing before is a different letter. So this is a letter, but if you changed one of these colors to green, let's say, it would be a different letter. So you have this enormous alphabet. The alphabet has many more letters in it than atoms in the known universe. You probably wouldn't get a chance to use all the letters. But then imagine you had all these letters, and then you were going to write some books. And suppose the books you write have you have a quintillion letters on each page. So each page of your book, you're allowed to choose, that's 10 to the 18th. You're allowed to choose 10 to the 18th different letters for this enormous page of your book. And then the number of pages in your book is a googol. There's a googol pages in your book. So there's more pages in the book than atoms in the known universe. And what I'm telling you is that a Googolplex is the number of different books you could write. So if you just went in on any page a googol -8, and just altered one of the dots, that would be considered a different book. There's a famous story by Borges about an infinite library, which turns out not to be infinite. And anyway, there's many fewer than a Googolplex books in Borges' library. OK, so that's a Googolplex. And then there's another way I thought maybe you might appreciate the description. If you so way back when, I talked about taking a cheese cube and cutting it in 10 ways. So if you took a 10 to the 98 dimensional cheese cube, so it's hard to describe what a higher dimensional cheese cube is, but it's sort of, you have kind of a line and then a plane, and then there's a third direction, and then there's a fourth direction, which you can't picture, and then a fifth, and then a googol directions, more or less. And then you slice it, cutting a googol rows in each direction. So you slice it as thin as like the number of particles in the universe, and then you let it fall apart. That's about a Googolplex cheese cubes. So this picture just sort of indicates how you might feel trying to describe a Googolplex. But then the one point I want to make is that in mathematics, people kind of have an ability to use language beyond the ability they have to imagine things. You can talk a lot about things that you can't quite imagine, and you can kind of formally work with them and make progress. Like a 10 to the 98 dimensional thing. You can't really picture it, but you can sort of work with it in a sense. So this is just supposed to indicate that if you just forget about trying to understand, or in a way try to picture things, and just think about language, you can sort of make much bigger numbers. And the idea is something called recursion. And this picture, this is supposed to describe what recursion means. It's like you take the original thing and then you put what you had back inside of it. So you take the smiley face, and rather than have eyes, it would have smiley faces itself. And then those smiley faces would have smiley faces. It's a way of kind of turning something back in on itself. So I'm going to go a little bit in the direction of recursion and talk about some bigger numbers. Maybe I'll write something on the board. Like 100 is 10 to the 2. And then a Google is something like that. It's 10 to the 10 to the 2. And then a Googolplex is 10 to the 10 to the 2. So you could, now you can't imagine that number, but you could imagine just putting another 10 down at the bottom and taking 10 to the Googolplex. People might call that, some people would call that a Googolplex plex. So plexing a number means you take the number and then the new number is 1 with that many zeros. So this next number, in the book I called it Fred, doesn't have a name. And what it is, it's you take 10 and then you take 1 with 10 zeros, and then you take 1 with that many zeros, and then 1 with that many zeros, and then 1 with that many zeros. And how many times do you do that operation, each of which is sort of bringing you, beyond anything you could imagine? Well, you do it 10 to the 10 times. So you do it like 10 billion times. So that's the number Fred. So there's, you can't imagine this number, but there it is. And then the next number, I called it Big Jim. And what it is, it's, again, you do 10 to the 10 to the 10 to the 10 to the 10. How many times do you do it? Well, you do it this many times. You do it Fred times. So you don't even know what Fred is. So you're taking one, but this number is kind of small in the scheme of things, because you could imagine making a tower of these things where there was like a billion of them, or this number of them, and so on like that. So you could have sort of a tower of these 10 to the 10 to the 10s where the tower was, Fred high, and so on. And so, you can't picture these things, and but you could make little symbols like sort of maybe Fred would just be like 2 boxes with a 10 in it, and then Big Jim would be three boxes with a 10 in it, to indicate that you're sort of making like three towers like that. And then you could make numbers where it's like boxes and they go in a bunch of times, and then the number of boxes is described by other boxes, and so on like that. And you could make up a new symbol which said how many times you did this. So, well, okay, the conclusion from all this, I suppose, is just that that's the end of the book. Infinity is farther away than you thought. Somehow it's not like it's just like 1, 2, 3, and you get, it's just you have to kind of imagine these numbers, and then there's infinity sort of way, way out there. Okay, so now I said before that now the talk is going to kind of start. When you see the cow, it's going to start back at the beginning. So now I want to talk about kind of infinite numbers in a way. Like what is an infinite number? Well, I'll say what this could possibly mean. So this is another book I wrote called Life on the Infinite Farm, and it's going to be also published by the American Math Society, which is the same publisher that published the Really Big Numbers book. And you can't read it yet, but in print, but it's on my website. If you just go to my website, then there's a link to it. So anyway, I wanted to introduce some of the animals on the farm, and then talk a little bit about some of the things that you get with infinite numbers. So this is Gracie, and she's got some feet, some more feet, more feet, more feet. Anyway, she goes on forever. So the cow, you know, she has no back end. There's no tail to the cow. And, you know, this presents a lot of problems. Like, for example, how does Gracie live on the earth? And I indicated that she doesn't actually live on the earth. She's encountered the earth, and, you know, she doesn't know what it is. So you have to sort of imagine a kind of a flat, infinite plane that she lives on. And then there's a lot of problems people wonder, like, where did she come from? How did she get there? And I guess my answer to you is that she came from the north. She just sort of steadily moved. Then there's Hammerwood. Hammerwood is a crocodile with an infinite jaw, and he likes gum. So I thought one thing is the way he's chewing, living on an infinite place. Imagine you've got this crocodile that's got these open arms, and they go out forever. So now suppose he's chewing in the usual way. Well, around where his mouth is, the arms aren't moving that quickly. But further out, they're spreading really, really rapidly. It's a little bit like if you took a flashlight and you were sort of moving it around. If you were shining the light on the back wall, the dot would be moving very quickly. Or maybe it was a laser pointer. But if you were sort of shining it across town and you moved it a little bit, the thing would move extremely quickly. So anyway, if she's kind of chomping up and down on her arm, like way, way, way out there, the thing is moving, you know, her jaws are just moving at an incredible speed. So, you know, not to mention maybe crashing into other animals and things like that. So I'd sort of imagine she was sort of chewing like in a kind of wave, sort of like where her mouth would kind of go up and down. His mouth. Anyway, so there's the chicken, Paddington. This is sort of the chicken drawn in perspective. It's like this is sort of supposed to be like a vanishing point. So again, like the teeth just kind of go on forever. This book presented a lot of physical problems, like he has an enormously strong neck, for example. So anyway, if you look at this picture, so he's missing some teeth. It looks like he's missing some teeth. And so I want to give him some braces. And now he goes through a couple of year period where the braces tighten his teeth and they bring them together. So if you actually picture this, you might imagine the teeth are kind of slowly coming together as they do for braces. If you've ever had braces or have a sibling with braces, you know that they don't move very quickly. But in this case, you know, towards the end, like out like a Googolplex or one of these big number, Fred or Big Jim numbers, the teeth are just zipping along at an enormous speed. Okay, well, after a couple of years, it's all good. And so the question is, does he have more teeth? How many of you guys think he has more teeth than he did before? Same number or more? See, they're missing before. Some are missing. And then, yeah, Elena? 2 times more. He has 2 times more. Looks like he has twice as many teeth. Seems reasonable. So here's a kind of an idea that he doesn't have any more teeth. Well, the braces are just kind of moving the teeth, and so it's not changing the number of teeth. They're just kind of moving closer together. And I even made this little chart where here the first teeth, you know, the first tooth, I called them 0, 1, 2, 3, and here they're 0, 2, 4. And here's 0, it gets matched up with 0, and 1 gets matched up with 2. There's a way to kind of match up the teeth. Like if you wanted to know, are there more, say, children or balloons? Well, you could try to match them up. Give each kid a balloon. And are there kids without balloons, or are there balloons left over? And a way to say that there's the same number of kids as balloons is that there's a way to exactly match them up. So for the teeth, I've sort of matched the first one to this one, and then this one to this one. And so you could argue that really there's the same number of teeth, whatever that number is. Kind of, it's like an infinite number, but still, whatever it is, it seems that there's the same number. On the other hand, it also looks like there's twice as many as before. So what do? Well, I thought I would give the same example again with the Croc. He likes to chew gum, but if you look closely, it's not so pretty. He doesn't brush his teeth very often. There should be a moral in every lecture. And teeth fall out. And so after a while, he's missing teeth. He waits, maybe like every other tooth falls out, or so he doesn't have as many teeth after a while. And then ants come along, and they attach rubber bands to his teeth. And then for technical reasons, the first few rubber bands are attached to a stick by his mouth. And then there's a period of time where the rubber bands contract like braces, and then he's happy again. So again, you have to imagine these rubber bands kind of coming together. I guess if they weren't attached to the stick, it's kind of hard to imagine what would happen. Like which way would the teeth move? Sort of, maybe they'd go this way, or I don't know. Anyway, so he's happy. He's got all his teeth. Okay, so now I'm going to explain a little bit. Actually, the only reason why there's words here is I couldn't figure out how to get them out of the book. But George Cantor, maybe 150 years ago, got this idea of talking about infinite numbers. And it was this matchup idea. Like for finite numbers, you would say that two numbers are the same if you could match them up perfectly. So it's like 3. The number 3 is sort of a name for all the different things that go bup, bup, bup. Like there could be 3 chairs, there could be 3 people, 3 basketballs. And the way you know that they're the same number is that you can perfectly match them up. So Cantor got the idea that you could say what an infinite number is it's all the things that you could match up the same way. Like if you go back to the way back here to the chicken, here are all the numbers, all the counting numbers, 0, 1, 2, 3, etc. And here are the even counting numbers, 0, 2, 4. And according to Cantor's definition, they'd really be the same kind of, they'd be like representatives of an infinite number in the same way that 3 basketballs are representative of the number 3. And this is a way of kind of showing you that really these are the same number because you can match them up perfectly. So this is what people sometimes mean by an infinite number. Oops. Okay, so I had imagined in my book that Cantor was this guy who was jumping out of an airplane. Somehow it's like this kind of, it's a simple idea to try to talk about like the sizes of infinite numbers, but it's this kind of breathtaking leap in a way. So anyway, he jumps out of the plane. There's a close-up. And then there's a question you could ask, which is like, okay, there's obviously more than one finite number. There's 1 and there's 2 and so on like that. Is there more than one infinite number? So like, is there more than one size of infinity? So what I'm going to try to describe for you is what they call the Cantor diagonal argument. So in the next page, I call it the famous, he's going to push a button, the famous Cantor diagonal argument. So I'm going to try to show you that there could be more than one size of infinity. So this is going to be the only mathematical proof in the talk. So brace yourself. So firstly, here's another picture of the chicken where he has sort of a different number of teeth, I claim. And so what I'm here, maybe I'll draw this on the board. Actually, let me see what time it is. You guys know it. I want to see how much. I'm just 11:35. OK, great. There's time for Cantor's argument. OK, so the way to think about this is that where are the teeth in this picture? Well, you've sort of, if you want to locate a tooth, it's like you can either sort of go here or here. And then once you're there, you could sort of decide that the tooth is in here or in here. And then once you're there, you could decide whether it's here or in here. And so I'm imagining that you can't even really see the teeth. They're infinitely small. But to get to them, you sort of make some choices. Like you either decide to go to this branch or this branch or this branch and so on. And so a way to describe this more mathematically, okay, is that there's this kind of there's kind of the 0 part of his mouth and the 1 part of his mouth. And then there's inside the 0 part, there's a 0 part and a 1 part. And again, there's a 0 part and a 0 part and a 1 part. And if you want to locate one of his teeth, you have to specify. It's a little bit like you're driving home. And you say, well, first turn left, and then turn right, and then turn left, and so on. It's just that your home only appears after an infinite number of steps. And only then the steps kind of keep getting smaller and smaller. So once you get to your house after making like 5 lefts and a right, they tell you you're not done. You have to go to your bedroom. But then you say, well, you have to decide which bed you go to. And then you have to decide whether you go to the back of your bed or the front of your bed. And so you have to keep making choices. You're not allowed, you never get to rest. You just keep making choices. So what I want to say is that one of his teeth is really a string of these numbers, like 0, 0, 1, 1, 1, 1, 0. That's who knows? Maybe that's one of his teeth. Another one maybe goes 1. Maybe one of his teeth is all 1s. Another one is maybe 0, 1, 0, 1, 0, 1, 0, 1. I'll do a couple more. You could think of all the different patterns you could make. And I want to try to convince you that you can't, these things are called binary sequences. And I want to try to convince you, like, if you look at all of them together, there's no way to just match them up with the counting numbers. Like, you can't say, this is the first tooth, and this is the second tooth, and this is the next one. Like, there's too many to try to match them up. And so this is what people call a proof by contradiction. You say, well, let's explore the possibility that we really could line up all the teeth, match up all the teeth. People would often say we can count the teeth. Like, you count the first one, and then the next one, and then the next one after that. And so I'm going to sort of explore the possibility that you can. And then I'm going to show you that there's some tooth that's not on the list. And then, but you said, wait a minute, you put them all on the list. And so that's a contradiction. It means that you couldn't have done it in the first place because if you're not familiar with these kinds of arguments, they're all over math. Maybe in law it's like that too. When you're trying to convict somebody and you're saying, well, listen, you're trying to defend somebody and you're like, it's absurd that my client was at the scene of the crime because actually he was in Las Vegas that night. So sort of like his presence in Las Vegas is contradicting the assumption that he was at the scene of the crime. So I'm sort of going to contradict the idea that you can list all the teeth, all the infinite binary sequences. So let's explore the possibility that you can. So here it is. They're listed. Maybe this is the first one, and this is the second one, and this is the third one, and so on. So for this argument, you have to agree that they're all listed. I've listed all the teeth. So here's what you do. You put a box around the first one, the first number in the first row, and then you put a box around the second number in the second row, and then a box around the third number in the third row. And you keep going like that. So you can imagine that I've written these things on the floor. Maybe like each horizontal row is one of these tooth names or binary sequences. And then I'm walking down the diagonal, and I'm just recording which numbers I see. So what do I see? I see 0, and then 1, and then 0, and then 0. Who knows what I see? But now for the magic trick. What you do is you make a new sequence, a new name of the tooth, where you just read what numbers you have, and you switch them. So the first one was a 0. I switch it to a 1. And then the next one was a 1. I switch it to a 0. And then the next one was a 0. I switch it to a 1. And then a 1, and so on like that. So let me just say it again. You've got this kind of whole arrangement of all the tooth names. They're all listed. And then I just walk down here, and every time I see one, in my mind, I just switch the number. And this is giving me a new tooth. So this tooth name better appear on the list, because I've listed them all. So where is it on the list? Well, could it be the first one on the list? No, because it's wrong in the first place. Could it be the second one on the list? No, because it's wrong in the second place. And then it couldn't be on the third, it couldn't be on the third one, and so on, like that. So this new tooth, or this new name for a tooth, supposedly it is on the list, because I was able to match them up, supposedly. That was my kind of assumption. But then it's not on the list. So now you might think, well, maybe there's just a little bit more. So maybe I could just adjust my list, like, stick this one in there. But no, you already agreed that they're all on the list. So, not only is there one more, it's not that there's one more. This is because if there's one more, you could just open up the list and put it in. Or even if there was half as many, you could just do what I did to that guy's teeth, sort of expand the list and put things in. No, there's like so many more that there's nothing you can do to line them up. So this is one of these things that all mathematicians know, and people learn sometimes in high school and college, that there's more than one size of infinity. Sort of an amazing thing. It should be, in the book I say it should be something that should be shouted from the mountaintops. And then it goes on. There's a more sophisticated, you might think that's it. Like the number of this guy's teeth, well, that's sort of like 1, so to speak. Actually, people don't know if it's 1. There's something called the Continuum Hypothesis. They don't know if there's a size of infinity that's like smaller than this number of teeth, so to speak, and the other chicken's number of teeth. Nobody, in a sense, it's not they don't know it. It's that you can't prove it from the usual axioms of mathematics. But anyway, it goes on. You could there's a similar kind of argument that shows that there's another infinity and then another one after that. And so there's this kind of endless tower of infinities. And then there's a tower of infinities, and so on like that. So it's sort of a surprising picture of numbers. So I wanted to give you another view of this size of infinity. So I was sort of imagining a guy who's an artist, and he's going to make a finger painting. And well, that's what he looks like from the side. That's what he looks like up close. He's sort of unusually, he has the property that the closer you look, the more intricate he gets. So that's what his hand looks like in the beginning. And then it goes like this, and then like this. And each time his fingers keep branching. And then the last thing he does is he takes his fingers and he dips it in paint and he just touches the paper. And the number of dots is that all the binary sequences. Okay, so I'm just finish up. I just drew some other pictures where what people might look like if they had sort of this size of infinity features, like that many eyes and branching hands. And that's another one. He's carrying this other infinite set. And then finally, have a nice day. Okay.